Hello, everyone. Welcome to a demo on using a recurrent neural network. As you learned about in the lecture, recurrent neural networks are a way of processing data which inherently has some sequential aspect to it. So generally, this is used for applications like text, and then we have a paragraph or a chapter or lots and lots of words, and we process the words over time. And it's insufficient to apply a network just to a single word because it wouldn't have any meaning out of context. So we need to we need to apply a network to several words repeatedly. And we don't want to apply a single neural network to like simply 10 words because the size of our paragraph or our sentence could change over time. So we want to pass in a sequence where the length of that sequence is variable. This is also the case when it comes to audio data. So if we are processing some sort of uh, music or song that's been recorded or someone speaking, again, it's important to have context over time in order to process that. And we can think of this as sequential. And there's also just generally other types of time series data, such as financial information or any kind of market that changes values over time. Today, we're actually not going to be doing it on any of those. We'll be returning to our favorite data set, which is image classification. We'll be doing image classification on the fashion MNIST dataset. So you thought you were done with it, but we're not actually done. The reason that we're doing that is because all of these other applications tend to require lots of encoding. So before we can apply a network to a word, we need to do something to encode that word into a numeric form in a vector. And we haven't yet covered how to do that, but we will soon in this class. The same idea for audio. It's not clear how to go from a representation of a clip of data of an audio into something that we can apply a neural network to. And also, yeah, same thing for time series. But luckily, we are very good at image classification loading this data so far. So we'll see how we can apply recurrent neural network to it. Okay, so let's go over this picture, which is the whole idea of a recurrent neural network. If you think about just this image on the left, this part of the image on the left, we have some input, xt I minus 1, and it goes through some neural network, and we get out ht minus 1. And this should be very familiar to us. We have some neural network which takes an input and it outputs something. Now, to make this recurrent, the only thing that we need to do is output this same thing, but also pass it into the next layer, or not to the next layer, into the next neural network when we process the next time step xt. So in this case, you can think of xt minus 1 as a word, and xt as the next word that appears in a sentence. And when we're processing this next word, we take in that next word, and we also take in the output that we had from the previous, when we process the previous word. We combine this information, concatenate it together, and then we apply a tanh, a neural network, a single layer with a tanh activation on top of it, which will put it to the range minus 1 to 1, which we then output. And then we repeat this process when we apply the network to the next input, xt plus 1. Now, the advantage of this approach is that we can keep around information from previous steps in our process, in our sequential data, without actually storing it. And without actually processing it all together. Just the hope is that we learn weights in this network so that the information that we're passing in is useful to us for the final prediction task that we're going to do. And oftentimes it has to be useful for us because the task is something like determining whether the sentiment of a sentence is positive or negative. In which case, a single word doesn't do that in isolation. You have to pass in important information from the previous words in order to solve that task. Now, as we discussed, the issue with a recurrent network is that you can overwrite the prior information. So if it's really important that understanding the context of this paragraph means that I understand the very first word of the very first sentence in the paragraph, this approach won't work so well for me because I'll overwrite that information as I pass it through this network. I overwrite it again and again, and I'm simply not able to keep track of it. That's because there's no way to directly pass information from xt minus 1 to xt plus 1. It has to go through the network at this step. So one solution to this is using an LSTM, which stands for long short-term memory. And I'll put another graphic here and we'll talk through this graphic. Okay, so this graphic with an LSTM, maybe I'll write that out. Long short-term memory. When we have this, we're able to keep track of information from prior time steps. And the idea is hopefully we'll be able to solve the problem where we need context from a while back in the process. Notice that this is similar to a regular recurrent neural network in the sense that we have an input xt for some value of t, and we output ht. And so it's a regular neural network in that sense, except now we're doing something slightly different, which is instead of just passing the output ht minus 1 to the next time step and concatenating it, we also pass another version of the vector, which ideally will keep track of longer term information. So we can make some sort of output here. This will get overwritten again and again because we need to change what our output is for each one of these steps. And we also have another vector representing some longer term information about this process. So let's walk through intuitively which each one of these steps do. And maybe I'll write this out. So maybe I'll write it out down here. Okay, so each step in LSTM. This first step down here, we apply sigmoid activation. This is the one that looks like the Greek letter sigma, to our input concatenated with the prior output. This gives us values in the range 0 to 1. That's what the sigmoid function does. And then we multiply this element-wise with what we've been saving so far. When we multiply this with our history vector, that's how I want you to think of the thing that we have on the top. This is like deciding what is worth keeping around. So sigmoid outputs something that's close to 0 and we multiply it, then that's like we're deleting it from our history. If we sigmoid output something that's close to 1 and we multiply it, then it's like it's keeping it around history. Okay, so this does some updates based on our current values to this history vector. The next thing we do is we multiply a sigmoid activation with a tanh activation. Tanh is like sigmoid, except it outputs values in the range -1 to 1. So a sigmoid and a tanh multiplied together gives us something that are in the range -1 to 1, or it could be close to 0. And then we add this to our history vector. This is like, so sigmoid times tanh gives values in range -1 to 1, which are then added to our history vector. When we add it to our history vector, that's like figuring out what's worth keeping around. This is like figuring out what's worth keeping around in our history. Okay, so far we've done 2 updates to our history. We've deleted some stuff here, and we've added some new information there. The next thing we do is apply a regular neural network to our input and the prior output, just like we did in our recurrent neural network. And we also apply a tanh to our history vector, and we multiply this with these 2 things together. So we combine our history vector with the current state of what we have at that moment by multiplying them together. And this gives us our output vector, which we then output to ht, and we pass into the next iteration of this network. So the third thing we do is combine history and current state vectors to create an output. Okay, so this is what's going on in the long short-term memory. And the thing that's really worth keeping in mind is that we have this other history vector that we're passing along on this top level. And the idea of that is that we keep historical information, which will be helpful for us when we're doing the prediction task of outputting ht. Excellent. So one thing that this kind of obscures but is very important to keep in mind is that each one of these graphics, each one of the times we apply the network to something in our sequence, it's the same weights. So the weights here on this linear layer with a sigmoid activation are the same as the weights here for this linear layer and this sigmoid activation. These things are shared. So this may seem very complicated and like we need to learn a lot of weights, but actually we don't. You only need to learn one of these networks and the weights for only one of these, and then we apply the same network again and again and again. Now, you might think that this becomes quite difficult when we do backpropagation because the same weights are appearing multiple times. If we take the derivative of this, the output with respect to these weights, it changes a little bit because of the process here, and then it also changes again because changing the weights here changed the output that then gets input to this version of the network, which then changed this output. We won't cover it here, but there's a way of dealing with this called backpropagation through time. And with that, I think we're all set on what long short-term memory is and how it's different from a recurrent neural network. As promised, we won't actually apply this to data such as text or audio because the encoding is very difficult. We'll instead apply this to our image classification with our MNIST dataset. So I'll say, because we need to encode text and audio data, we'll apply the LSTM that we just discussed to image classification on our favorite fashion MNIST dataset. We've seen this several times, so I'm just going to copy this code. This code will load this dataset. We import a few libraries, and then we get our training data. As we normally do, we just specify training equals true, and we do the same thing for our testing data. I'm also just going to copy some code which will allow us to plot these images. As usual, it's very nice and satisfying if we can plot the data that we're working with and gain some understanding of what we're working with. As usual, in the fashion MNIST dataset, we have different clothing items. So for example, 3 looks like a dress, and 7 looks like a shoe. And each one of these is labeled with a number between 0 and 9, representing the type of clothing this belongs to. And the task is, given one of these images, we want to classify it as one of these numbers representing which type of clothing it belongs to. As usual, we'll also create a data loader with the training data set and the testing data set. In this case, we'll set our batch size to 100 and we'll shuffle through all of this. Okay, so the tricky thing that we need to figure out is first, how are we going to pass in an image to our LSTM or our recurrent neural network? Because inherently an image is something, in this case, which is 28 by 28, and it's not clear like how we want to pass it in. One thing that we could do is pass in one image and then another image and another image, but actually there's no point to that because there's not necessarily a relationship between this image here and this image over here. So we don't want to pass in multiple images. We somehow want to partition one image and pass it in pieces. One way to do this is to pass in a single row at a time. And that's what we're going to do. So we'll pass in this first row, which is just the pixels at the very top. Then we'll pass in the next row, which are these pixels at this next level, and so on and so forth. In this way, we've turned an image, which we normally think as one data point, into lots of different data points, one for each one of the rows. And because each row is already a vector, we can just pass in that vector into the LSTM, and each one of those rows will correspond to an XT. It'll be XT minus 1, XT, XT plus 1. Okay, so that's how we transform our image data set into the format that we need for our for an RNN or LSTM to be able to process it. So I'll say passing image data into RNN. Key idea, pass in each row in the image as a different quote unquote data point. Okay. To do this, I will import some nice libraries as usual to work with Torch. And then we'll set different parameters. I'm setting them here just so we can talk through it. The sequence length, this is the number of things we have in our sequence, is 28 because that's the number of rows we have in our data. So if we just look at, I think we call it image, and we look at the shape of this image as usual, it's 1 by 28 by 28. This is the number of rows and this is the number of columns. So when we pass in the data, this is 28, this is the number of things in our sequence, which is the number of rows. The next thing we'll pass in is the input size. This is the size of each one of the things that we're passing in. This is also 28 because the shape of image is 28 by 28. So it just so happens that the number of rows and the number of columns is the same. The number of columns is the size of each one of the rows that we'll pass in. This is the size of each row, which is 28 pixels in our case. The next thing we'll specify is the hidden size. This is the size of this history vector that we pass through the network. You can set this to whatever value you want. Here, I'll set it to something that's nice and large, like 128. This is size of the history vector that we were talking about in the LSTM. The number of layers, you can think about stacking copies of this LSTM on top of itself. And that should generalize nicely. It's just instead of passing in XT, you pass in HT, and you also have versions of the prior output and the history vector here. And just by making this network deeper, we make it richer, and hopefully it'll be able to fit the data better. So we'll choose the number of layers to be 2. This is stacking LSTMs on top of each other. So you can imagine a different layer to that figure that we've been referencing. We have some batch size. I think we actually already set the batch size. We set this to be 100. So we just want to make sure that this lines up. We'll have the number of epochs that we're training for. We won't train it for so long because we don't want to use a lot of compute. And we'll also set a learning rate, which is quite normal at 0.01. Okay. Now that we've set all these things, let's define the RNN that we'll be using. I'm referring to it as a recurrent neural network because this is a broad umbrella term which also includes an LSTM. But sometimes we also use RNN just to refer to a more simple version where it's nothing of this fancy history multiplication addition is going on. We simply have a single value, but in this case, I'll use RNN to refer to something which also has an LSTM inside of it. Okay, so we will initialize this. We'll pass in the input size, the hidden size, the number of layers, and the number of classes. In our case, that's the number of classes in our data set, which is 10. We'll inherit all these properties. And then we'll keep track of the hidden size, the number of layers. I type? I hope so. And then we'll also have a version of the LSTM. Luckily, we don't have to implement any of this. It would be a little bit complicated to do that. We'll instead just initialize this, and we have an input size, a hidden size, the number of layers, and batch first, which just specifies that when we pass stuff into here, we will have both batch size and sequence length. So in our case, when we're saying batch first, that just means the dimension of what we're going to pass in is batch size, sequence length, and then the input size, which is 28. Notice that this is actually what we normally pass into the regular neural networks that we apply to this task. It's the same thing. It's batch size, number of rows, number of columns. It's just we're thinking about it slightly differently when we're passing it into this RNN, and we'll see a benefit of thinking about it in a slightly different way. And then for the final layer, we'll initialize FC, which is just getting us from the hidden size which we're passing through our LSTM to the number of classes that we have. When we call forward, again, the size of X is batch size, sequence length, and input size. We initially, the very first time we run this, we'll need to have some vector that we're passing in up here. That's the hidden dimension, the history vector, and the prior output. Because that's what this network needs to run. We need to pass in this input and then also these two history vectors. In our case, we won't have anything here, so it's normally standard to do something like passing in just zeros in this case. This would correspond to having no information about what's going on. The size of zeros will be the number of layers. So we need to have one of these for each one of the layers in our LSTM, which in this case is 2. And the dimension of this will be the size here, which is the input size. This, I think, we should have this as self.input size. And just so happens that that was okay because both are 28. And then C0 is equal to the same thing. So I'll just copy it. Okay. Now with both of these vectors, the prior output and the prior hidden layer, we'll pass this in. And we'll get an output from our LSTM, which is the output and our hidden layer. And we'll do that by running X and H0, C0. Implicitly, what this will do is it'll do the whole pass on our whole sequence. So instead of just applying it once, it'll apply X, it'll apply the network many, many times to all of the different input values here. So all we need to do is call this in order to get the output for running on each one of the values in the sequence X. And we'll get some output, and we'll also get this hidden layer. We don't really need the hidden layer, so we'll just get another, our final output will be the linear layer applied to this output, which is the things we need in the output are actually just the very last value. So there will be lots of things here. So yeah, maybe let's specify the size at this point will be batch size, sequence length, and hidden size. When we output stuff here, oh, that's interesting. It's disconnected. The thing that we don't need all of the outputs at this point because there will be one for each one of the things in the sequence. We just want the very last one here. So the only thing that we care about is batch size, and I'll say last output of sequence, and then we still have the same hidden size, and we apply a linear layer to it, we'll get, and because the linear layer goes to the number of classes, we'll output something which has the dimension batch size num classes, which is all we really wanted in the first place, because what we're going to be doing is comparing how we're like whether we're able to classify this image using the final output of our RNN on this sequence. Okay, so now that we've defined this code, we'll initialize our model with the input size, the hidden size, the number of layers, and the number of classes. Let's print out our model to see what's going on here. Oh, right, it looks like it took so long to code that just got disconnected. Oh, num classes is not specified. Num classes should be 2. Okay, so we get exactly what we were expecting. This has input size 28, hidden size 128. There are 2 layers of it. We specified the size of the input features. This matches the hidden size out here, and we use this linear layer to go to a dimension of just 2. Okay, so now let's do some training on this. Training. As always, we'll define our loss function. Here, I'll just copy this code because I think it's really standard, and our optimizer. Because we're working with classes, we'll use cross-entropy loss. We will, maybe I'll walk through this. So we will train the model. For epoch in range num epochs, we'll do our favorite thing, which is using the enumerate function to get an index, our data, from our training data loaders. In the forward pass, we'll get our outputs, which is our model applied to this squeeze. There's a singleton channel that we're just going to squeeze out here. This is remove singleton channel. We'll compute our loss function. This is loss func applied to the outputs and the labels. And then we'll do our backward pass. And this we've seen many times, so we'll also just copy that. And it looks like I messed up labels there. And this should all be on the same. Okay, cool. So when I run this, I get an error, of course. And then object has no attribute input size. It looks like that's something I didn't save here. Okay, so needs to be equal to. Cool. Let me see if that. Oh. Expected H hidden zero size to be 2, 100, 128. We got 2, 28, 128. Okay, so the order that we're passing something in is wrong here. Let's check that this is input size, hidden size, number of layers, batch first. Input size, hidden size, number of layers, number of classes. This is input size, hidden size, number of layers, number of classes. Okay, that's weird. I don't want to do this on the fly, so I'll just copy this code. If it's correct it. Num classes is not defined. Equals 2. And let's see if that hopefully fixes it. Oh, that's right. Target 3 is out down. Number of classes. Oh, sorry. Number of classes is not 2. Number of classes is 10. That was the issue. Sorry. Okay. Cool. Sorry about that. Oh, and we're about to run into an error, which is I didn't define what total step is. This is just the total number of steps that we'll be passing here, which is the number of epochs times the length of the data loader. Okay, cool. Sorry about that. Okay, so we're loading and training this model. We should hopefully soon see the training output. This will take a little bit, so I will pause the video and get back to this when this finishes. Cool, so this finished running, and it lasted 6 minutes. That's because we're not using a GPU, which is fine. The loss goes down, it starts at 0.68, and it decreases over time until it gets to 0.3. It's not very stable, which suggests maybe we should have used a slightly higher learning rate, or just that this is a difficult problem to use in RNN for. Let's test our code. I'm going to test the model that we just trained on the data. I'll set this to be val so it doesn't keep track of gradients, and also do this so it doesn't keep track of gradients. And we'll count the number of times it gets it right, and then total number of images that we have as we go through the testing set. So 4 images labels in the data loaders test. We will apply our model to the images, to the squeezed image for this. So that's model applied to images.squeeze. And we get we will look at the outputs. These are values, and using torch.max, we'll get the indices of the ones that are largest of outputs data along the first axis. We'll add up the number of these, so the size of this, and we'll count the number of ones that we got correct. So this is the times that predicted is equal to the actual true labels. And we sum this up and take that single scalar value, and at the end we'll print out our test accuracy. Let's run this. So print f test accuracy. This is total. And then we'll say percent after this. It looks like we get 88.13% accuracy, which is pretty good, on par with the prior methods that we used. One thing that's worth noting is that this approach takes longer than the prior methods that we used for this. The reason why is that we can't parallelize much. So anytime we're processing one of these images, we need to process the first row. Once we process that, we can get the hidden dimension in the output and then pass it into the model that we're going to use for the next row. So really, we have to do this 20 different times for each one of these batches of images, which makes this process slower, and that's the reason that this takes longer to run. Okay, but so we finished this, we've looked at the accuracy. Let's see, so far, it seems just that we've done a more complicated thing for the same task that we know we already can solve. But let's imagine that we can't see much of an image so far, so we're only looking at part of the image as we go. And let's see what happens in this case. So I'll choose a particular index, let's say it's 32, and I'll choose that image from images that we just defined here. I think we called it images. Okay. If we look at image and the shape of image, this is 1 by 28 by 28. We will crop this image using some number of rows. So let's just look at the first 10 rows, for example. The cropped version of this image will be that we will take the first dimension. We won't take all the rows, we'll just take the first num rows, so the first 10 of them here, and we'll take all of the comments. This is our output cropped. We'll apply the cropped image here, or yeah, we'll apply our model to image cropped. We'll get our predictions here. So we take the max of output on crop on the singleton dimension. We get the first one of these. We just want the indices. We'll turn that to items. And then we also will want to get the label. The label will be the same one in the still the 32nd one. Oh yeah, this is called output cropped. And then let's plot this. So image cropped squeeze. And see what happens. Tensor 0 elements cannot be. Oh, right. That should just be 1. Okay. And then plot the show, and then we can turn this into a gray color map so that it doesn't look as weird. Okay, so so far we're looking at some item of clothing. From this alone, I'm honestly not sure what this is. We can look at some more. Let's look at 20 of the rows and see if we can figure out what this image is. Okay, it looks like it's pants in this case. But me, it took like, I don't know, maybe we could have told that at 15 rows to figure out what this is. Maybe less, actually. Maybe 12. Yeah, it's starting, now that I know it's pants, it's starting to look like pants. But let's see how the model does. So we can print out the predicted label. That's the thing that's predicted. And then we can also print out the true label. And hopefully these things will line up. When we do this, the predicted label is 3 and the true label is 4. If we give it more information, oh, it looks like it's pretty bad. The predicted label is 1 and the true label is 4. Let's give it all of the rows. It still thinks it's 1. Let's go back and look at what 1 is. 1 is pants, and it's saying the true thing is 4, which is sure. Wait, is that right? That seems very silly. True label is 4. Oh, maybe I didn't run this again. Oh, okay. Sorry, for some reason, I guess that didn't. I'll just put all this code here, so it will definitely run next time. Okay, so yeah, no issues. This is doing the right thing. Let's see if it has 10 rows. It's outputting label 3, but it's really 1. It looks like label 3, if we go up here, is address. So at 10 rows, it thinks that this is address, which honestly to me is pretty conceivable. If we give it more rows, 15, looks like it gets it right. We can try a different image, and this time we can test ourselves. So initially, let's just give it 4 rows. Based on this, I'm not sure what it is, but it looks like it's predicting 3. The true label is 4. We give it 5 rows, it looks like it got it right. And 4, if we go up here and compare, it looks like is a shirt. So amazingly, this model has been trained well enough that without even looking at a full image, only looking at a partial image, we can get the correct label. Now, I'm not saying that this is something that's necessarily very practical in practice, but it's very cool that instead of having to pass in the entire image, we can pass in only part of it. And because of the way the LSTM works, this is enough information for us to generally figure out already what's going on. We can try this for some other images, the third index. It's making a prediction, but there's nothing in this image so far, so we probably have to give it some more rows. Still, it doesn't look like we've gotten anything so far. I can tell that this is a shoe so far. It looks like it needs 20 rows, maybe? Did I just try 15? I'm not sure. Yeah, okay, 15 rows, it figures out that this is a shoe. At 13 rows, it thinks it's index 9. Index 9 is a boot versus a shoe. That's very subtle. Or wait, is 8 a purse? No, it looks like 8 is a purse. Oh, 5. 5 is the correct thing. 5 is that sandal or heels? 9 is shoe. 5 is sandals. Okay. So those classes are already very similar to each other, which just seems like it'd be very challenging to tell them apart. And we'd also need information about the bottom of the sole to make that decision. But anyways, I think this is very cool, and hopefully you've gotten a better understanding of the way that recurrent neural networks work, LSTMs, and how we can yet again use the fashion MNIST dataset in this class and in these demos. Links to everything, or the links to the notebook, are in the description of this video, and you can follow along. Should have said that yeah. Thanks very much.